First, I want to talk. Do you have any questions about the last time or about something else? Hmm? Mhm.
Why do we decompose it? We put 1 over 2f.
Under this computation is under the function delta of t squared minus r squared. It is by definition delta of f of r, which is sum over f of Rn equals to 0 over zeros of this function f, 1 over absolute value of f prime of Rn, delta of r minus Rn. And in this particular case, we just apply this. To r is the derivative of absolute value of derivative of r squared. So, anything else?
We derive with respect to f. So why we take the function f of l and not f of t?
Because it does not matter in a sense when we integrate something that depends on t and on r with this delta function. The first integral already gives just some function of t or some function of r. So we are free to choose whatever variable we want. So. So in principle, so if you want to make everything rigorous, you can write this under the sign of integral with the arbitrary test function and do all this. But the only difference will be in the order of integrations. So. So it really doesn't matter. So, or you can say that this delta function is a delta function on some submanifold. Actually, mm, Actually, I don't think how to say it in some invariant way, but probably it can be doable. In a sense, you can write that it is a delta function on some submanifold, and there is some normal coordinate and tangential coordinate to the submanifold, and you can write something in the multi-dimensional case. But maybe it is easier just to say that we choose some coordinate. Okay, so let us go further. So some reminder of what we know. Last several times we were speaking about Green functions of different equations, and we'll continue doing this today. But I also tell about some other things, some tools which can help to rederive some of this Green function that we already know and compute a few new ones. So what we know? We know the Green functions of the heat equation. Minus Laplacian of u equals to some f. So we know it for any d. We also know the Green function for the Poisson equation. It's also for well, RD, no, also for any dimension. And we also know again functions of the wave equation. Uh, this is for d equals to 1, 2, and 3. Because in higher dimensions they become more and more complicated. And there is one case which wasn't covered here. It is a grand function of the Helmholtz equation. So, namely lambda squared minus lambda m squared minus Laplacian oh, sorry. So Laplacian u equals to f. So we would like to find this grand function at least for some dimensions, but actually we can write it for arbitrary dimension to see the new special function, namely the Bessel function or modified Bessel function. So some parameter. I yes. So it, if you consider some a quantum field theory in the Euclidean space, it will have a meaning of mass. But here I just say that it is some positive number. Yeah. So in principle, there is also Klein-Gordon equation where we have the where we have D'Alembert operator in a sense second time derivative minus Laplacian. So it's called Helmholtz. And this is called Klein-Gordon. And we will not consider this equation because it is so the level of complexity of this is a kind of a sum of levels of complexity, or maybe a product of levels of this and of this one, because we see that when we work with the wave equation, its grand functions have some complicated behavior. For example, there is this 1 over square root, which is continued by 0 for bigger values, like outside the light cone. In some dimension there are delta functions, so there are some functions that have singularities on big submanifolds, and in this case we will have some special functions. So this equation, so green functions of this equation have both singularities on some submanifolds and special functions in the explicit expressions, and moreover. The precise values of these green functions in coordinate space are, so in most cases are useless. So people mostly work with the Fourier transformations. So, but and actually the problems which are formulated for this equation are usually different. So here we formulate some initial value problems or boundary value problems, but in this case people find green functions that are symmetric. For example, they're they're more useful usually. Okay, so Today I want to compute gain function for this equation. So And to do this, I want to tell about Laplace operator in spherical coordinates. By the way, have you ever seen some explicit formulas for it? Hmm? Do you remember it? Uh, Mhm. Minus or plus? Yeah. Mhm.
And then there is the angular part, which is the angular momentum.
Mhm. So 1 over r squared Laplacian of theta phi, right? And this Laplacian of theta phi, do you remember it? Mhm. Inverse. Oh, 1 over sine theta and d theta sine theta d and d theta. And the second part, right? Yeah, so there is this formula, and in principle, you have a reason to derive it. In a sense, there is this explicit relation between Cartesian and spherical coordinates. But I want to show some way to derive this formula for Laplacian, which can be used also for other coordinate systems. So, idea is the following: we can we know that if we consider a scalar product of gradients of two functions, f gradient g, so integral over some integral over some space r to the d. Dx. So it equals to minus, so we can integrate it by part and say that it is minus f scalar product with Laplacian of g, right? In each variable. Advantage of such approach is that if we want to change a coordinate system, we should do it not for the second order operators, but for the first order operator for this gradient, and also for the volume element. Suppose that we want to compute this minus f Laplacian of g. No. Maybe let us better compute this scalar product of gradients. So gradient of phi, gradient of g in polar coordinates, in spherical coordinates. So let us draw a picture. So there is this, maybe it's better to draw some bigger picture about. I can draw it here. So there is this angle phi, there is a angle theta, and this projects here. So now we can introduce some local so XYZ. So now we can introduce some local orthogonal coordinate system such that one axis is parallel to radius, another axis is parallel to xy plane, and is orthogonal to this one. So let us call it some 1, 2, and the third axis is a third axis lies in this plane and is orthogonal to the first two. Like. So if we change phi, then we move along this second axis. So we can write that delta x2 equals to r phi times sine of theta. Delta phi sine of theta. Delta x1 equals to just delta r. Delta x3 equals to r delta theta. So is it okay? So imagine that we change theta a little bit, and since this since this is so since this third axis lies in this plane rotated by angle theta, and we rotate the radius vector precisely in this plane. It's the only coordinate which is changed up to the second order.
So we're using Helmholtz appreciation.
Yes. So they can kind of infinitesimally small. So using this, we can write that this gradient is a sum from I equals 1 to 3 delta f over delta xi delta g over delta xi. So So in total, it is uh, 1 over r squared sine squared of theta d f over d phi d g over d phi. Plus this term 1 over r squared d f over d theta d g over d theta plus just df over dr dg over dr. So having this, we can write that integral of Laplace of gradient of f. So are there any questions about this formula? That's fine.
Is that the gradient with the denominator gradient or Laplacian in the first after the summation?
So they are deltas. Maybe I should use different notation for delta. It's usually used for variational derivatives, but here we can confuse everything with Laplacian, so it's better to use this curly deltas.
Okay, so it's the variation associated with the small variation the x1, the x2, the x3.
Mm-hmm. Yes.
Why use the variation in delta and then use the operator of
I'm just saying it. So I'm sending these variations to 0.
okay.
So just a picture to write this formulas. So we imagine this infinitesimally small variations of all coordinates and write the derivatives in there. So this will be an integral with this volume element r squared sine theta d theta d phi dr times df over d phi d g over d phi plus and now we want to integrate all this by parts. So because we should have a minus f Laplacian of g in the answer. This can be easily integrated because it does not contain phi in the measure. So it is the integral r squared sine theta d theta d phi dr. So this is minus 1 over r squared sine squared of theta uh, f d to g over d phi squared. Here we should be careful because this derivative does not commute with the sine of theta. So we should write minus 1 over sine of theta d in d theta sine of theta d g in d theta. So this sine of theta is this sine which was there, and this one is recovered to cancel this sine in the measure. And in the last part we have the R squared. Hmm? Yes, I forgot F. Yes, it is here. So and here we will have F 1 over R squared d R 1 over R squared dr R squared d g in dr, maybe d in dr. So, and if you look at that formula, we see this precisely. Because, so there is a radial Laplacian and the singular part. So we'll study the singular part later, but now let us think about the radial Laplacian. By the way, if we work with a two-dimensional space, then it will be just Laplacian will be dr 1 over r. Oh, maybe let me write it in this form: dr plus dr squared plus 1 over r dr plus 1 over r squared dphi squared. Because in that case, we will not have all the signs in this measure. So we will basically have only these terms. We can do all the same. But in general, there is some angular part and there is a radial part. So this radial part is d r squared plus d minus 1 over r dr. Precisely because of the form of the measure in the spherical coordinates. Or without these arguments, we can just act with Laplacian on some function that depends on square root of sum of xi squared. So this is a sum of dxi xi over square root of sum of xi squared f prime of this. And when we differentiate, we have three options. We can differentiate this f prime again, so it will be f 2 primes times sum of xi over square root of sum of xi squared squared, which equals to 1. And then then there will be f prime times sum of 1 over square root of sum of xi squared and there will be f prime sum of xi squared over sum of xi squared to power 3 over 2. So this expression, so sum from 1 to d, and here also sum from 1 to d. All the sums are from 1 to d. So, so this sum equals to d over r, and this sum equals to minus 1 over r, because sum of xi's equals to r squared. So, and if we take all this together, we get that it is f2 primes plus d minus 1 over r f prime. So we can derive this radial part of the Laplacian operator just by acting on some function that depends on only on radius. So it's another maybe the simplest way to compute this. So, are there any questions about this? If so in principle there are hyperspherical coordinates which can be written recursively, and we can write some formula, although I don't remember precisely how it looks like, but it should be something of this nested form, because here we had some Laplacian of a smaller sphere. So where is it? Yes. So there is this. There is a angular Laplacian for a smaller sphere, then it is included in the angular Laplacian of bigger sphere, and I think it should have a similar nested form, but I don't remember if I wrote it at any moment. Okay, so we have this radial part, and I am paying some attention to it because in some cases this formula can be written in a different form, which is useful. And namely, there is a case when d equals to 3. And in this case, this Laplacian r of f can be written, of course, as 1 over r squared dr, r squared d in dr, r squared df in dr. But you may also check that it can be written equivalently as 1 over r d2 in dr squared of r f. So is it clear why it is true? Because u v 2 primes equals to u 2 primes v plus 2 u prime v prime plus u v with 2 primes, right? So, and the second derivative of r is 0. So the term which we could have in principle just vanishes. So and this formula is nice. It says us that this radial part of three-dimensional Laplacian is actually conjugate to a one-dimensional Laplacian. So so so, so this formula can be applied in the following way. Uh, Suppose that we are solving, for example, the wave equation. So uh, we have some dt squared minus Laplacian of r acting on u equals to some f of t and r. And now let us use this formula for the Laplacian. So dt squared minus dt squared u minus 1 over r d ru in dr equals to f of tr. So and now we simply multiply everything by r and get so d2 in dr squared dt of ur dt squared minus dr squared of ur equals to r f of t and r. So we see that 3D wave equation. So 3D radially symmetric wave equation is equivalent to 1D equation on a half line. R is greater than 0 because it is a radius, just positive. So and I suppose that we solve this equation for some green function, for example, where we have some delta functional source on the right hand side. Or suppose that we are solving this equation for some right hand side that is located at 0. So we have something at 0 and free equation on the other space. So So we have such a wave equation. So equation for UR looks like some equation for a string uh, with some initial with some boundary condition at 0. R U and there is some better to say that so it is UR, and here there is some UR of 0 of 0t, which is some function equals to some oh, of t0 equals to some function phi of t. So in the sense that we have some boundary condition and we have some waves that propagate in positive direction. So do you remember how to solve such problems with boundary conditions on half line? How to write a solution for the wave equation? Hmm? Oh, let us also say that it is 0 at some moment. Oh, basically, I want to say that this UR of no, R U of T and R can be written as a phi of T minus R or R minus T, maybe T minus R. Hmm? So it's some question about behavior of this Laplacian of this function at 0. In a sense, there will be some delta function, and the nature of the delta function is precisely the same as the nature of delta function on the right hand side of the Boston equation, because we have a singularity 1 over r at the origin, and because of this we have some delta function. But
So can we do this, or we can also keep us saying prolong with the assume that, for example, at some distance tau function is 0, and then prolong by symmetry, and then use D'Alembert formula.
for what precisely?
For the one-dimensional problem on the whole line.
In a sense, how to get this answer?
Yeah.
For me, well, in principle, yes, but for me, some easier way to think about this is just to say that this function gives precisely what we want. So it definitely solves this equation and gives precisely what we want. When we put r to 0 equal to 0, it gives this dependence, and it is 0 otherwise. So. So, we can write now the formula for this u of t and r. It is phi of t minus r over r. And mm, you might notice, of course, that we obtained this formula for a delta functional source at the origin. But in that case, it was divided by 4 pi. So this 4 pi, in principle, should be derived from this local analysis around 0. But if we are interested in just in some solution, we know that this solves the wave equation in all points except for 0. So, so it's solution of the 3D wave equation. And
So basically, the solution to the three-dimensional problem is the initial perturbation which expands in time, getting in the having small amplitude for a long distance.
small, you mean separated by 1 over r?
By 1 over.
Mm-hmm. Yes, yes. So in some sense, this wave almost preserves its form, and there is no uh, no infinite tail in that case. Mm. Mm. So you see, even if we don't knew we don't know anything about the Fourier transform, we would be able to find this formula using simply some variations of the D'Alembert formula for 1 plus 1 equation, and we would also be able to integrate it in one of the coordinates to get this green function for d equals to 2. So, there is some shorter path to this expression without this Fourier integrals. So, are there any questions about this? So, and now let us finally apply this to the Helmholtz equation. So first, the most trivial example, d equals to 1. So there is in this equation m squared minus dx squared f equals to delta of x. So and we are looking for solutions that decay to infinity. So what are such solutions? So what is the solution of this equation for x is not equal to 0? Maybe let us say that for x, and we are looking for x greater than 0 and x less than 0. How? Oh, and so, but what will we get?
But the other side is positive, so it should be exponential for exponential.
But what kind of exponential? With what?
The Gaussian.
Hmm?
The Gaussian.
No. Why? So if you take exponential of dx squared of e to lambda x, or what is this?
Oh no.
So it is lambda squared equal lambda x. So exponentials are eigenfunctions for derivative operators.
Should be I think
But if you ask it to decay at infinity, it should be minus mx, some c plus, and here, yeah. Mm-hmm. Yeah, thanks. So, but now we should say something about this c's. Actually, if they are different, then this function will be discontinuous, and if it take its second derivative, it will be in the best case a derivative of the delta function. So we should say that they are uh, so that this function is continuous and equals to c at 0. Um, now let us compute derivative of this function. So f prime here equals to minus cm e to minus mx, and here equals to cm e to the mx. So we can say that it can be approximated by the we can just write that f prime equals to minus m sine function sine of x e to minus m absolute value of x. And actually, this function was e to minus m absolute value of x. So if we now take a second derivative, we will need to take derivative of the sine function, and we know that derivative of the sine function is. But by the way, what is it in terms of generalized functions? D in dx of sine x. What will it be? Hmm?
the principal value. The P.
No, why?
Because
A principal value is for 1 over x. It's for the friend of delta function. It's a function, it's a generalized function that goes to infinity at 0, but it goes to plus and minus infinity on different sides, so we can integrate it, compensating these two parts. But here, so if you take x different from 0, just 0. It's derivative of constant. Hmm? No, but more precisely, integral of delta function equals to 1, and integral of this function equals to what? Oh, 2? Mhm. Yes, because it is 1 minus 1. Mm-hmm. Yes. So f2 primes equals to, I also forgot c here. So f2 primes equals to minus 2cm e to m minus m absolute value of 2cm delta of x. And actually, we can differentiate also this exponential. So it will be plus cm e to cm squared e to the minus m absolute value of x. We will have square of a sine function. And this is m squared times f. So taking all this together, we see that f two primes. So we see that m squared minus m squared f minus f prime equals to 2cm delta of x. So c equals to 1 over 2m.
Why do we have the sign of x in the second derivative of f?
So why it disappeared? Or because we differentiated absolute value of x. So the derivative of the absolute value of x. Yes, a sine squared equals to 1 because it's 1 for positive and 1 for negative.
Sorry, why x second instead of 1?
Because we differentiate this as sine of x and get 2 times delta function.
Yes, but we have to multiply the first again.
But we multiply by some function that equals to 1 and 0. And we have this a formula that f of x delta of x equals to f of 0 delta of x. Right? Because it does not know about the value of this function in all other points. Okay, so any questions on this? Is it fine? Okay, so there is this computation saying that so we can write the answer. So g of x minus x prime equals to e to minus m absolute value of x minus x prime divided by 2m. This is for d equals 1 a Helmholtz for this equation. So, are there any questions? Yes. So let us do the same for d equals to 3. So, so we want to solve this equation: m squared minus dx squared minus Laplacian f equals to delta of r. And since the delta function is radially symmetric and also boundary conditions are symmetric, we just ask this function to go to 0 at infinity. Maybe it's better to call it g. Since everything is radially symmetric, we can write that it is m squared minus radial Laplacian times g equals delta of r. Or in other words, it can be written as m squared minus dr squared of r times g equals, so it's complicated. It's not very mm, clear how to write this delta function in radial coordinates, because this integration measure is non-trivial. So it is easier to say that we solve this equation for uh, r different from 0. And when we go to r equals to 0, we can just use something that we know about Poisson equation without this m. So let us just solve this equation. So what will be the solution that goes to 0 at infinity?
Rg
Mhm.
equals to e to the minus
Mhm.
mr over 2m.
It is some other question about the overall coefficient. It will be different. So we can just put some constant here. So we see that this grand function is now c e to minus mr over r. And we can expand it as a series in m. So it behaves like c over r minus cm plus all of r. So there is some singular part which is proportional to r. To one of, which is proportional to this constant, and there are all these corrections. So comparing it with the Poisson equation, we can figure the singular part, because its grand function starts from 1 over 4 pi. So this one should also start from 1 over 4 pi. Or it is 3D Poisson. We can say that the grand function is e to minus mr over 4 pi r. So yeah. Yeah.
Why is the constant different? Because like with the symmetry, we deduce the problem to a problem in one dimension, like we did with the wave equation. So shouldn't the solution be the same?
But the question is how to pass from a three-dimensional delta function, which is one when we integrate with this measure to one-dimensional delta function. So first, there are some questions about the power of R, which can be resolved. But second, this integral, if you pass from 3D integration to 2D integration, will contain the volume of the area of 2D sphere, which is 4 pi. So probably we can write it somewhere that uh, integral of r squared dr d theta sin theta d phi of some f of r equals to 4 pi times the integral from 0 to infinity dr r Or maybe better to write two functions, g of r, f of r, dr rf times rg. So, and I think this should be an explanation. But it is always hard to think about these delta functions written in spherical coordinates because, for example, r goes from 0 to infinity. So in some sense, we will have some 1/2 of the delta function. So it is something tricky, and for me it looks that it is easier to solve everywhere except 0, and then see what precisely happens at 0. So, so are there any questions about this? Mm-hmm.
What is the G, the the bottom label?
Hmm? A solution of this equation.
What is
It is in this again function. Oh,
so it is the solution of the Helmholtz equation in D equal to 3.
yes.
And why compare it with the third one?
Hmm? Oh, so what? What the question? Can you say? Ah.
No, I didn't understand why you have to compare with the 3D Poisson.
Because it appears simply if we neglect this m squared term. So this term does not produce singularities because we simply multiply with it this function. So singularities come from Laplacian, and so to compute this delta function contribution, we need to act within this Laplacian on this 1 over r term. 1 over r itself is regular at 0 because integrals with 1 over r are not divergent because of this integration measure, r squared. So, the only singularity appears when we act with this Laplacian on this 1 over r. So, and we also see that if we put m equals to 0, we just recover the gain function of this Poisson equation, as it should be. And by the way, this function is called the Yukawa potential. It appears, for example, in the interaction of some massive particles, when some interaction is carried by the massive particle, or also in the in some plasma where we have charges screened by the other charges. So. But it can also appear if we consider, for example, the usual wave equation, but with some wave equation or heat equation with some, for example, periodic boundary conditions. But we will talk about this later, I think. Yes. So now we know this Green function for d equals 1 and d equals 3. The question is, what happens for d equals 2 and in principle for other d's? Right? So, are there any questions about this? Not. Okay, so maybe we can go further, right? So maybe let me raise this. Okay, so arbitrary dimension. So in this case, we are solving the problem m squared minus Laplace times u equals to times g equals to delta of r. Uh, so who can tell the formula for the Fourier image of this gain function? G of r, g tilde of p. What is the formula? That's what happens if we do a Fourier transform of this equation. No, in a sense, this is defined by this equation. Can we just write a formula for its Fourier image? If, hmm? We know that G solves this equation, and we can imagine that it is represented by the Fourier integral. We can say that G of r is the integral d p over 2 pi to power d e to the I pi r g tilde of p. We can take the substitute into this equation.
We think it should be e to the minus ir p ir dot p maybe
Who is r dot?
scalar product. Okay, over m squared minus p squared.
But each time you take second derivative of this, you get a factor I pi, ip. and here it is minus 1/n.
two times, I think.
Hmm?
So minus I to the t because we are doing.
No, two derivatives.
Ok. Two times. Due meno fanno 2i fanno meno, quel meno fa più. Ok. Plus.
Mm-hmm. Yeah, it's almost fine. So the question is, who is R? Because so if I put here minus R0,
Yeah, it should be R.
then it will be fine. So let us actually think. So yes, if we substitute it here, we get R minus R0. Yeah, thanks.
Yeah, and the denominator is pi squared.
No, what?
Or just pi. P.
Yes, yes. Mm, mm. But we actually want so this so solution of this equation depends only on the difference of R minus R0. So we put R0 equals to 0 because it's a translation invariant. So it will be just 1 over m squared plus p squared. So, mm. Okay, so let us substitute this formula here for R0 equals to 0. So it will be the integral d p over 2 pi to power d e to the I p r 1 over p squared plus m squared. So you see, if we substitute, if we keep R0, we'll just have the difference, R minus R0. So it will be a function of R minus R0. So it's easier just to keep a single variable. So we have this, and one of the standard ways to compute such integrals is to raise this denominator, which is quadratic function of p, in the numerator. So, namely, it is done by this substitution. So it's, for example, a trick which is used for the computation of Feynman integrals or Feynman diagrams. So it is very popular. So we substitute as the integral from 0 to infinity d lambda e2 minus lambda p squared plus m squared. So is it clear that it's equivalent formula? Okay, so now we can exchange integrals, and we see that the integral in lambda is now Gaussian. So it is integral from 0 to infinity d lambda e2 minus lambda m squared and integral in p. Or pi to power d. And it actually should remind you something, because this is precise the trick that we did with the green function of the heat equation to get a green function of the Poisson equation. And the only modification here is that we also have this prefactor e to minus lambda m squared. So otherwise it's the same computation. So so now we can compute this integral in p. Some transformation.
The first part we can put 1 over m squared.
Where 1 over m squared.
The integral is from 0 to infinity, so the result.
No, it's this times some function of lambda. Lambda is here, so we will need to compute this later. So, so here we should subtract IP over 2 lambda, IR over 2 lambda squared minus R squared over 4 lambda over 4 lambda, like this. So so now this Gaussian integral can be computed, and it will be integral from 0 to infinity lambda e to minus m lambda squared so this is a lot of computation of this Gaussian integral, and there is also this exponential minus r squared over 4 lambda. So so it is 4 pi to minus d over 2 integral from 0 to infinity d lambda e to minus m lambda squared minus r squared over 4 lambda. And also got lambda to minus d over 2.
But this will do factor 1 over 5 to be in the was in the okay. There
We have a square root of pi to power d from the Gaussian integral.
how much is the Gaussian integral?
So,
Okay.
and if we have a lambda, then it will be pi over lambda. Okay, so Hmm?
Should be an exponent of the exponential. If before it was lambda and square, then it became m
Ah,
squared times lambda.
yes, yes, thank you.
Uh,
So, it is also useful to write this formula and that coefficients here and there are the same. To write that lambda equals to mm, 1 over 1 over 2m r over 2m times lambda tilde. So if we substitute it here, it will make this coefficient 1/2 uh, uh, times mr and the same coefficient there. So uh, overall it will be uh, 2 pi r over m to minus d over 2 integral from 0 to infinity and the tilde lambda tilde to minus d over 2 e to minus m r over 2 lambda plus lambda inverse. Like this, or we can write it equivalently as 2 pi. It's lambda tilde, but just integration variable. And I write it as integral from minus to plus infinity. mm, as d tau. So I make substitution. Lambda equals to e to minus tau. So e to tau. So, so it will be e to tau 1 minus d over 2 e to minus mr uh, cos of tau. So there is some there is this integral of this kind, and it is code up to some prefactor, which I don't remember precisely. This is a code uh, k of d over 2 minus 1 of mr. And this is called a modified Bessel function. So this particular function is called the McDonald function, if I remember correctly. In this case, so so for example, when d equals to 0, when d equals to 2, this uh, uh, actually, sorry, I wrote this part in some wrong way. There is this. There should be also some term that comes from this change of variables. So there will be also uh, just r over 2m. Yes. Hmm. So when d equals to 2, and then this gain function equals uh, uh, to 1 over 2 pi on this k0 of mr. But if d equals to 3, and in principle it works for arbitrary odd dimensions. So in this case, we can say for 3, also for 1. So for d equals to 3, we can say that this gain function is some factor like 1 over uh, hmm, pi to 3 over 2 maybe. Or maybe let us write it with some arbitrary coefficient. Let us write that it is some uh, square root of m over r times k 1/2 of mr, which in this integral. So it's on one side, and on the other side we know the formula. So some coefficient. We know that it equals to 1 over 4 pi r e to minus mr. So we see that although it is not obvious that this integral can be computed, it actually can be computed, and we can find this uh, we can find this closed expression. But this is some function that is not known explicitly. We can only study its properties. And by the way, it is also easy to see why we have this duality between d equals to 3 and d equals to 1. Because for d equals to 1, this factor equals to minus 1/2. For d equals to 1, it equals to plus 1/2. For d equals to 3, it equals to minus 1/2. And we can simply change integration variable from tau to minus tau. So it's uh, the same function.
This works for every d such that symmetrical with respect to the other.
Yes, in a sense, this McDonald function is symmetric with respect to inversion of this index. Hmm? Some constant, so some powers of pi, so this stuff. Well, let me write some 2 to some power pi to some power. What is it? Hmm? Hmm? Hmm?
After the first change of variable, why the factor before the integral?
So there was a lambda here. We had to multiply it by r over 2m and raised to power minus d over 2. So I just combined these two. And there was also simply d lambda. So, so we get this prefactor. I forgot it originally. Hmm?
But the change of variable there should be r over 2m to the power of d.
Uh,
No,
why? Mhm. Hmm?
the modified Bessel function is only the integral, or is also r over 2m times the integral.
No, only the integral.
So,
Hmm?
what are the properties of this one-time Bessel function? Like, how does it behave for big dimensions?
So no, for big dimensions, I don't know. In that case, there will be question. What is the region of our interest? Because um, uh, maybe it will be trivial to say what is small argument, what is a large argument if you take a big dimension. So, but actually, no, maybe a good approximation will be that it is just some decaying exponential times some power of r, maybe something of this kind, because uh, non-modified Bessel functions of high orders look like trigonometric functions. In some sense, it can be explained like this. So since half of these functions, no, not half of them, but these functions for half integer indices have explicit expressions as trigonometric functions at times some powers of r, then we can use this series to look at some asymptotics. So it will be basically some exponential plus some power law corrections. But more interesting questions are to find asymptotics of these functions around zero and around infinity, and also find connection formulas that relate solutions with different asymptotics around zero and around infinity. Mm. So, mm, because let me actually say more about the equation they satisfy and so on. So these are functions that satisfy some second order equation. So we have this function. We have also function that grows exponentially at infinity, like it was in this case, like the second solution. And we can ask, for example, how to relate this growing and decaying solutions to some solutions at zero. And if you ask about the asymptotics of this function at 0, then they simply behave as some power of r, because this integral can be so this integral is again function of a Poisson equation. So for big m's, it is this exponential asymptotics.
Okay. Because I want to this function that you allow weights property allow no weights, but solution to this equation propagates in higher dimensions. So the fact that it goes decreasing like exponential means that the solution propagates harder in higher dimensions.
But this decay rate is almost dimension independent. Like the main factor is e2 minus mr. The dimension enters only in the power of r in the denominator.
Yeah.
So,
So it's true in general.
Yes.
In this case, it depends.
What do you mean?
In the sense that for every dimension, I have a different function.
Mm-hmm.
And when the dimension is larger, I have my function decay exponentially in the dimension.
Like if you take r fixed and some dimension.
Exactly.
Yes.
Yeah,
Yes, it is true, but I'm not sure that it is the only limit we can consider, and that it isn't the best limit. Because, for example, we can have r scaled by this dimension, or by some function of dimension. So we can ask, for example, some quantities to be finite, and only after this send this dimension to infinity. So. So it depends on a particular problem. But technical tool to compute such integrals with at some big R or big dimension is usually a so-called saddle point. Actually, no, maybe I will tell about this at the end if I have time. But before this, I wanted to say that such functions are actually solutions to some equation. Right? So, are there any other questions? Um, So, so the question is, what equation is satisfied by these functions? And this k, well, let us write k and d over 2 minus 1. So we were looking for the green function. So it was on this radial Laplace equation, dr squared plus 1 plus d minus 1 over r dr, and the function that we should substitute here is r to power 1 minus d over 2. Sorry, I forgot this massive term. Minus m squared r2. acting on so in principle, we can rescale this variable r by m, but maybe it is easier to put m equals to 1, because in any case, everything depends on m times on m times r. So let me simply do like this. So we know that it is 0 except for 0, but we don't care about 0. There will be some singularity, which can be considered separately. So now let us act with these derivatives. So r squared first differentiates this twice, so it will be r2 minus 1 minus d over 2 times 1 minus d over 2 times minus d over 2 k, just k. Then there will be 2 times a product of two derivatives. R2 minus d over 2 k prime, such term. Then the last term is second derivative plus r2 1 minus d over 2 k primes. Okay, so it was about a second derivative. Now this first derivative, d minus 1 over 2, so just d minus 1, and we first differentiate this r, it will be 1 minus d over 2 r2 minus 1 minus d over 2 k plus d minus 1 r minus d over 2 k prime, and the last term in that one minus, so it's for the first derivative, minus r1 minus d over 2 k equals to 0. Okay, so it's some big expression, but there are just some numeric coefficients. Let us take all of them together. Oh, probably can erase this. Okay, so the first term, which is proportional to r minus 1 minus d over 2, it contains minus d over 2 plus d over d squared over 4 plus d minus d squared over 2 minus 1 plus d over 2, writing that term from the second part. So in this expression, and then what about in k prime? Here it appears with a factor 2 minus d, and in that term it's d minus 1. So it will be just r2 minus d over 2 k prime. Well, this cancels almost completely. And there was that last term with different power of r. R2 1 minus d over 2 times k equals to 0. So let us take these terms together. So it will be so it is minus d squared over 4, then the power of d plus d minus 1. So it is minus d over 2 minus 1 squared. So, and if I also multiply this equation by this factor, then it looks like, I also forgot second derivative of k. So plus r to 1 minus d over 2 k with 2 primes. So we have this, and we have minus d over 2 minus 1 squared plus r squared times k d over 2 minus 1 equals to 0. So if you now replace d over 2 minus 1 by some number nu, if you denote it by nu, then we can write this equation like r squared k nu 2 primes plus r k nu prime minus nu squared plus r squared k nu equals to 0. And this is called a modified Bessel equation. And since we already have some way to find the solution of this equation by that integral, we have this differential equation together with the integral representation of its solution. So otherwise we would need to guess the solution somehow. For example, one way to get it is first to find some series expansion of solution of this equation, and then try to resum this series and present it as some integral. Uh, After we do this, then we can look for other solutions which can be obtained by analytic continuation of that one. In the sense that if you have such an integral, and if you want to check that it really solves some differential equation, we just act with this differential operator, and this integral becomes an integral of some derivative of some function, and it vanishes if this function vanishes at the end of the integration contour. So in principle, we can choose different integration contours in this formula, and they will give different solutions of this equation. Because at the moment we have only one solution given by this integral, but on this equation has more. And actually another much cheaper trick to construct a linearly independent solution is to say that for a new different from integers, maybe half integers, we see that equation for nu and for minus nu is the same. We have so we have two solutions, k nu and k minus nu. So if we go to integer nus, people also consider combinations. I'm not sure if it is precisely that combination, but idea is that we can consider something like sine pi nu k nu divided by sine k minus nu sine of pi nu. So it goes to something, some function of nu, when nu goes to 0, for example. So, yes, divided by sine of pi nu. So, so here is nu, here is minus nu. So they're only nu.
The same line that nu is different from
One half integers. One half times z. Actually, I'm not sure. Maybe it should work. Maybe we should exclude only integers. Oh, maybe just integers should be excluded. I forgot.
the ratio. K nu is in the argument of the sign or is outside?
No, it's a factor. Cosine of pi nu multiplied by.
It's like 1 minus cosine pi nu over 2 pi over sine pi nu all times k nu.
K minus nu minus this k minus nu divided by sine of pi nu. So the idea is that if we take if we are sitting at arbitrary nu, then we can take k nu and k minus nu given by that integral. They are perfectly defined, and they solve this equation. We already know this. And if we have some degenerate points when k nu becomes proportional to k minus nu. No, sorry. Actually, I'm saying no. Sorry, I'm saying about some different functions uh, because this function um, is symmetric under nu to minus nu. So forget about this part. Uh, to get yes, and so it applies only to some different functions like probably for I nu it works.
So this is not true for KU the way we define.
Yes, because this k nu is symmetric under nu to minus nu. It is a solution that
Okay.
yes.
Okay.
So
Okay. Okay. So it's not true for okay.
yes. Mhm.
There is a polynomial maybe expression for KU like this for other functions which are derived from differential equations, like Bessel function, Lagrange polynomials.
No, but what do you mean by polynomial?
Finite or series expansion.
Oh, series expansion, of course, exists because we can just take this equation and find this expansion.
Okay, so it's not there is no finite expansion polynomials. Finite.
Uh, no, finite expressions exist only for half integer nus. In a sense, a purely half integer, like for 1/2, like we saw here for 3/2, 5/2, and so on. So they are called basic polynomials. Uh, so the point we get some finite limit because if so well it's bad that we don't have any formula for this ice, but probably when we study Bessel functions we will see some explicit expressions. So there are solutions of Bessel equation or modified Bessel equation that become proportional when nu is integer and are independent for non-integer nus. So, so in this case, we can consider a solution which equals to this. So when nu goes to some integer point, I nu and I minus nu become proportional, and so numerator vanishes at a rate proportional to nu. And but denominator also vanishes with the same rate. So their ratio is well defined. And mm, no, it is a solution of Bessel, and it is defined also for integer nus. Actually, I forgot this k is precisely obtained in this way. Uh, so, uh, this the nature of this k or maybe this mm, yeah. I, I, mhm. Yes.
But
Mhm.
I nu and I minus nu are two solutions of this Bessel equation. Are two
Oh,
Bessel functions of this Bessel equation.
yeah, solutions of this Bessel equation which are not symmetric in mu. So if you find some way to write such function that is function of nu and it is not symmetric, then we can use it to write two independent solutions. But unfortunately, this is not the case. It is symmetric. So we are not getting this second solution. Hmm? Oh, yes. If yeah, if it is if we go to zero, then it should be k0. But I'm not specifying who these I news are because they are different. Hmm? But it's impossible to tell because I didn't define who are these eyes. I'm just saying that it can be obtained this way. So yes. So we will see this later when we study Bessel equation maybe non-modified. So. But the main point is that Bessel equation or modified Bessel equation will always appear when we study the radial part of problem. So, okay, so maybe that's all. Do you have any other questions? Yeah, by the way, concerning the possible integration contours in this function, you see that this hyperbolic sign can go to zero at different limits. For example, when tau goes to infinity or minus infinity, but also to infinity shifted by 2 pi in. And if you choose different endpoints, it will correspond to different functions. But maybe it's study this later. So, are there any questions? Yeah, thanks for your attention. See you tomorrow.